Welcome back everyone. In the last lecture we had seen how to control drones. Today we will be looking into how do we implement state feedback controllers practically, and for that we will have to understand a bit about digital control. Let's dive into that now. So far in this course we have been designing state feedback controllers for continuous time systems. We pick our desired closed loop poles, and then using the different methods that we have learned in this course, I can come up with a value or with the matrix K that will place the closed loop poles exactly where we want it to be. So now we are asking the question, how do we implement such a control law practically? Okay. Now in general what happens is, in the laboratory or in industry you will always find microcontrollers, DSPs or FPGAs on which you would like to implement such a control law. In such cases what happens basically? So notice that in such a case the the processor that you have will not have access to xt for every time instance. So basically what I'm trying to say is that suppose you have a processor, on this processor you want to implement this control law. So that means now this processor must get xt so that it can multiply minus k with it to give you minus k xt. But the problem is that this xt is a continuous signal now, so the processor will not get the continuous signal as input. So the processor is a digital device, so there will be sampling of this signal, and the processor will only get a sample of the signal, and the next sample will come at the next time instant of the sampling period, right? So between two samples the states will remain the same. So for example at xk you got some value of the state, and then from xk to xk plus 1 the value of x will remain the same, so it will hold that value, and the processor will multiply minus k, and then the output here will also be a discrete signal, which will then have to be passed through a digital to analog converter to convert it to UT, and then you can think of that, okay, can we use this UT in the actual system? Now you see, this is well and good. I mean, this looks like it might work, but there are certain issues. Okay, and the core question that's why we are asking is that how do we implement a continuous design correctly on a digital processor? Because the design that we had done was in the continuous time domain. How are we going to implement it on a digital processor which does not have, the digital processor does not have access to the continuous time signal xt? So the naive implementation is the one that I have just now explained. So basically I take samples of the states and I just keep on multiplying minus k with it, think that okay fine, the output that we will get, the ut that we will get uh, after converting this sample to a continuous time sample, maybe passing through a DAC, this will work for the system. However, there are issues here, because you see the UK that you are finding out, first of all will be a staircase type of an UK, right? Because between samples the value of xk is constant, which means UK will also remain constant between samples. If this is the sample kt, this is the sample times say k plus 1t, so between these two samples UK will remain the same. Okay, but had it been in the continuous time domain, this would not have been the case, right? So that means now when you are implementing this control law, this will not exactly work as you wish it to be. The problem is that this is not the system you analyze. What you actually have now is a sample data system. The plant is still continuous, x dot equal to x plus bu, but the ut is a staircase. This combination of a continuous plant driven by a input which is discrete is the problem. Okay, so its closed loop poles are not the eigenvalues of a minus bk now. Okay, they are the eigenvalues of some of a discrete version of the actual system. Okay, and that is the issue. So the closed loop poles of the discrete version of the actual system will not be the same as the closed loop poles that you have designed, and on top of that, even if a minus bk is stable, there is no guarantee that ad minus bdk will be stable. So we have a genuine issue now. Okay, so there is a chance that a naive digital implementation of a continuous gain can destabilize a well designed system. Well designed as in the design that we had done in the continuous domain. So in the continuous domain, it was a well designed system, right? There was no problem. But but when we are bringing in a discrete or a digital processor, then since because of sampling things might go wrong, and that is the reason we will have to be a bit careful while implementing this. Now there are actually different strategies to do this, but the strategy that I am going to follow in this course is the discretize then design approach. So basically we will discretize the plant first, and then we will design the K matrix for that discrete model. Okay, so let's try to see what that is all about. So I call the first part of this design as phase 1, or the offline phase, because this entire thing can be done just by writing a few lines of code in MATLAB or any other language that you wanted to write. So the step 1 is that you start off with a continuous plant model A comma B, and then you choose the sampling time. Now this sampling time has to be chosen wisely. So generally the sampling time is roughly 1/10 to 1/20th of, or the sampling time is generally less than equal to 1/10th of the real part of the dominant pole of the closed loop system. So the closed loop system that you had designed, you had dominant poles there. Check the dominant pole of that system, and the time period should be less than equal to 1/10th of the real part of the dominant pole. So for example, suppose you have designed a system of this form where the closed loop poles in the continuous domain you had placed at this point. Now that means in this case the dominant pole is this -2 plus minus j, and so therefore you should have at least 1/20. That the sampling period should be at least less than 1/20. That is how you can come up with the sampling period. So again, this is it's a thumb rule only. I mean, there's no limitation as to what you can take and what you cannot, but it is in general a thumb rule. Now the next step would be to discretize the model. So let's see how do we discretize the model. So when we discretize the model, the system x dot equal to x plus bu becomes a model of this form, which is now discretized. You can see that we will have only samples now. So what are these AD and BD? Let us try to look at that. So the system in the continuous domain will be x dot equal to ax plus bu. So we have a sampling time period say t. Then the solution of the system, we already know what is the solution of this. The solution of this is xt is equal to e to the power of a t x naught plus integration from 0 to t e to the power of a t minus tau b u tau d tau. This was the solution, and we take a sample of this solution. The sample of this solution would be something like this. So at the tth instant, what will be the value? So this will be what we get. So from here you will see that if I consider e to the power of at as ad, then this is what the expression will look like. Okay, so I am just dropping t now, because I can talk about the samples now. So the k plus 1th sample is nothing but the value of xt at k plus 1 into tth time instant. So I can drop the t now, and this is how the expression will look like. Here this part we are calling as ad, and this part we will call bd, because you see here this integration, in this integration uk I can take out. I take out the integration uk, and this part can be written in this way. So this becomes your ad, this becomes your ad, and this becomes your bd. Okay, so these are your ad and bd matrices. So once you have discretized the model, so then we move on to the next step, where basically the desired poles of the system, which we with the help of which we generally design the K matrix, the desired poles of the system also have to be now mapped to the discrete domain, and this can be done using a mapping of this form. So basically, if suppose your desired pole is say 2, then so suppose for example, if your desired poles are say -2 and -1, then your the discrete domain poles will become Z1 equal to e to the power of minus 2t and Z2 will be equal to e to the power of minus t. So these are your poles mapped in the discrete domain. Okay, this is how you can convert the continuous domain S plane poles to the discrete domain Z plane poles. Now once you have done this, the next step is finding out the K matrix, right? And this actually follows a similar structure like the Ackermann's formula. So this is the Ackermann's formula only. So here A and B has been replaced by AD and BD because now we are in the discrete domain, and this is the desired polynomial that you have. So this is exactly the Ackermann's formula. So using the Ackermann's formula we can find out KD, or you can also use the other methods that we have learned. So with that we can find out the KD matrix. So once we have found out the KD matrix, we just have to flash it to the processor as a constant matrix. Remember, it is very important for us to check whether the eigenvalues of AD minus BD KD, basically the eigenvalues of AD minus BD KD are nothing but the eigenvalues Z1, Z2 dot 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 that we have taken, and they should lie strictly inside the unit circle. So I mean, in general, if SI has been taken to be on the left half of the complex plane, they will come out to be strictly inside the unit circle. Okay. So stability in the continuous time domain, the poles have to be on the left half of the complex plane, but in the discrete time domain, the poles must be inside the unit circle. If you have gone through any signals and systems course, this should be obvious to you now. Okay. So this is the basic phase 1. So once you have passed KD as a constant matrix to the system, the processor does not know or care how it was computed, it just multiplies now. Okay. Now what happens in the real time now? So this part, whatever I have talked now, basically the part where I have found out KD has been done offline. So once I have found out KD, now we can move to the second phase, which is the real time execution phase. Okay. Now what happens on the processor at runtime every single sample period? This is what we will look into now. Now the first sample, so the first what will be done is the ADC reads the sensor voltage and converts them to state vector xk. So and it will be converted and it will be stored in a state register xk. So basically the whatever signal that you were getting, this gets converted with an analog to digital converter, and it gets converted to the sample xk. The processor then evaluates uk equal to minus kd xk. This is a matrix vector multiplication. This one is a matrix vector multiplication, and this can be easily done. And then once you have the uk, this is written to the digital to analog converter, which will convert this into ut. Whatever uk you had, it will the digital to analog converter will just convert it to a signal ut. Okay. So once you have that, so basically now you feed this into the actual continuous time system. So this is the total loop basically. So the basic structure is that you take AB matrix, convert them into AD BD, so that you get the discretized version of the system, and this can easily be done in MATLAB with C2D command, which will be using you will show that we will use this. So use that to convert it to ADBD, and once you have converted to ADBD, you also convert the poles that you have to discrete domain poles, the poles in the continuous time domain, or from the S plane to the Z plane. So then you find out the matrix KD using similar approach like a Ackermann's formula or something like that. You can go ahead and find out KD, and once you have found out KD, then it is a straightforward thing, because it is after that just multiplying KD with the samples of xk to get the ut. So this uk will then be passed through a digital to analog converter to get ut, which is a continuous signal now, and that will be fed into the system. Now the important thing is that the total computation time delta from the moment of sampling to the moment the DAC is updated must be less than the sampling period, because if the next sample comes before the ut has been calculated and sent out, then there will be a problem. So this has to be taken care of. Okay, so this is the basic idea. I mean, I'm not going much into details, but this is the basic idea. You will see that we'll implement this for a DC motor position control setup. Now, so in a DC motor position control setup, if you remember, so our transfer function was of this form. Okay, we have done this in the beginning of this course itself. So this is the transfer function, and if we consider that the inductor armature inductance is almost 0, then this becomes a second order system. And if it is a second order system, then we can write down the state space equation of the system considering the states to be theta t and theta dot, where theta t is the shaft angle and theta dot is the speed of the shaft. Input as armature voltage and output as theta t. Why I am taking theta t as output? Because I am going for position control, so I will take theta t as output. So using that, I can come out with the ABCD matrices. So these are my ABC matrices. What you can do is that you can go ahead and check that C SI minus A inverse B is actually giving you this. Okay, you go ahead and check this. You will find that this is the transfer function that you will get. So once you have the ABCD matrix, then basically it is one. Now that you have the A and B matrix, so then you can directly convert this to ADBD and then go ahead and implement the entire thing. Now, of course, you see in this case, the output has only theta t, so we will also need theta dot, because the entire state would be required. When we do this, we will need the entire state information. So therefore, we will estimate the entire state now with an observer. So we know what an Leuenberger observer is. You see, this is a Leuenberger observer, and the Leuenberger observer had this formula. Actually, you can go ahead and rewrite this formula in this way, where y minus y hat can be written as c x hat, and then if you take these things in, so at the end you can write down the same formula. This formula can be written down in this way, where this part will called as a nu and this part will call as b nu. I am doing this because we have implemented the position control of DC motor in using these equations, and that is why I am trying to keep it similar to how we have implemented, so that you do not get confused as to what we have done. Okay, so when you look at the implementation, you will see that we will be using a nu and b nu matrices. We will be using a nu and b nu matrices, and that is why I am showing you what a nu and b nu is. Okay, so this setup is nothing but this equation itself written in a different way. Okay, and also you will see that what are we measuring? We will measure all the states, right? That is why the C nu that we will take will be an identity matrix. Okay, so using this C nu, this A nu and B nu, you will see that we will implement this DC motor position control. Let's have a look at that now.
Hello everyone. Today we will be looking into the position control of a DC motor using a state feedback controller. So previously we have done an experiment in which we have estimated transfer function for DC motor using the input and the output data which we have collected through an Arduino in our Simulink environment, in which we have learned how to interface an Arduino hardware with our Simulink environment. So we are going to use the same Simulink block model of the DC motor into this experiment, and we are going to apply our state feedback control strategy to that very same block model. So as we can see over here, this is the same block model. This is the same block model that we have used in our previous experiment. The only difference is we are going to calculate the position instead of the speed, because we want to control the position of the DC motor. So we are going to multiply the encoder count with 360 divided by the PPR, which is going to give us the position of the motor shaft in degrees. So since we are going to use state feedback controller we need a state space model of the DC motor and also a Leuenberger observer in order to estimate the states of the DC motor from output that we are getting from the hardware. So the state space model equations are shown over here. We are taking position and velocity of the motor shaft as our state variables, and the ABCD matrices are given over here. Now, the equation of a Leuenberger observer is given here in equation number 15, which represents x dot equals a nu x plus b nu u, which is shown in equation 16, where the ABCD matrices of the observer, which is a nu, b nu, c nu, and d nu, are given from equation 17 through 20. So we are going to use this relations and we are going to provide uh, the values of the ABCD matrices in our discrete state space block in our Simulink model. Now we'll take a discrete time state space block and we are going to fill up the corresponding ABCD matrices based on the relationship that we have seen just now. So the output of this block is going to give us the states, the estimated states of the system, which is position and velocity, and we are going to multiply it with the state feedback gain matrix K. So the output is going to be subtracted from the reference that we will be providing, which is the shaft position which we want to achieve, and this will be multiplied with a pre-compensator gain in order to eliminate the steady state error. Now, this will be the input to the motor, but before providing this input, we are going to apply saturation block over here. We are using this to ensure that the voltage that we apply is within the maximum range of the maximum rated voltage of our DC motor, which is 12 volts in our case. So the saturation is from -12 to 12. So we'll provide this as the input to our plan and we will get the output, which is position of our plan. Now let us go to the code. So these are the motor parameters that we have taken from the data sheet of the particular motor that we are using. So we will be using these values in our state space modeling. So here is the ABCD matrices based on the relations shown over here. So once we have these ABCD matrices, since we are going to do this experiment, run this on Arduino hardware, so we are going to use discrete time model. So we're going to take a sampling time of 0.005 and we are going to convert this continuous time state space model into a discrete time state space model. So we are going to get the ABCD matrices in discrete time. Then we are going to provide the pole locations of the closed loop system, which is A minus B. And based on this pole locations, the response of our system can be changed. So for the time being, I will keep the pole locations to be -50 and -10. So the controller poles will be calculated in discrete time using this relation. Similarly, we will be calculating the observer poles, but we'll make sure that the observer poles are 5 times faster than the controller poles. We will do a quick controllability check. So if the system that we have modeled is not controllable, then the code will stop running at this point and show that the system is not controllable. Similarly, we will do an observability check. Then we will calculate the state feedback gain matrix K using place function, which does a pole placement of the system matrix A and the input matrix B and the pole locations where we want to place the poles. So taking these arguments, the place function calculates the state feedback matrix K. Similarly, we can calculate the observer gain matrix L since the system follows duality. So we can place for A transpose and C transpose and the required pole locations of the observer poles. So this part shows us the closed loop eigenvalues of the closed loop system, which is A minus bk. And this shows us the observer eigenvalues. And here we will be calculating the reference pre-compensator gain, which is n bar. This is required because we want to make sure that the system response tracks our reference without any steady state error. So now let us run this code. As we can see over here, we have got the state feedback gain matrix and the observer gain matrix and the closed loop eigenvalues and the observer eigenvalues. Now note that since we are calculating this for a discrete time system, the closer these values goes to 0, the faster the system should respond. So for the time being, it is 0.95 and 0.77. Now let us take these values and run our Simulink model using these values of K and L and see how the response works. So as you can see over here, this is the response. Now let us measure the overshoot and the settling time. So with the peak finder, we can see that the peak value is 108 over here. The reference is 90. Now for the settling time, we can see that the settling time is somewhere around 0.9. Now let us try and change the pole locations. So now let us change this value to negative 100. Remember, the further we go away from the imaginary axis, theoretically, the system should respond faster. So let us run this. And as we can see over here, the feedback gain matrix has changed. In fact, it has increased from its previous value. And if we see the closed loop eigenvalues, the eigenvalues has reduced. So it is going much closer to 0 as compared to the previous value. So now let us run for these values. As you can see, the response looks faster. So let us check it with measurements. So first let us measure the peak value. So the peak value now is 101. As we can see, it has reduced from the previous value of 108. Now let us check the settling time. Previously it was 0.9. Now it is somewhere around 0.6. So it has reduced. Now let us change the reference values to different position set points and see how the system tracks these references. So initially I have provided 360 degrees. So see, the motor has taken one full revolution. Now let us change it to 180. It should take half a revolution. See, it has taken half a revolution. Now let us change it to 90. Yeah. Now 240 degrees. And finally, let us bring it down to 0. So we have seen how we can perform position control of a DC motor using state feedback control. This time, what we are going to do is we are going to calculate the state feedback gain matrix K using the linear quadratic regulator, the LQR problem. In order to use the LQR problem, what we are going to do is we are going to minimize the cost function J, which is given over here, and we are going to find out uh, the optimal control law, which is U of k is equal to minus of k x, where k is the state feedback gain matrix, and we are going to calculate this by minimizing this cost function J. So in order to do that, we have to solve uh, the discrete algebraic Riccati equation given in equation 26, and once we get the value of p from the discrete algebraic Riccati equation, we can calculate the value of k using the equation given in 25. Now, in a similar manner, the observer gain can also be calculated using the LQR method, since the system follows duality. So instead of calculating the LQR for A and B, we can calculate it for A transpose and C transpose to get the observer gain matrix. Now, the Simulink block model is similar to what we have done in the previous experiment, where we have used a pole placement method in order to calculate the value of K. Now, going into the code here is almost similar to what we have used in the previous experiment. The only difference is, instead of using the place function in order to calculate the K and L metrics, we will be using the DLQR function, which stands for discrete LQR. So we are going to provide the A matrix, B matrix, and the weighing matrix Q and R as the input arguments, and this function is going to calculate the K based on the LQR. So similarly, we can calculate the observer gain matrix using the LQR method. So instead of A and B, providing A and B as argument, we will be providing A transpose and C transpose as our input argument. So we shall see how the response of the system change by changing the value of Q and R over here, which is the design parameter of this control method. So we are going to change the value of Q and R. Accordingly, our response of the system is going to change. So first off, let me start by making Q to be an identity matrix, just 1 and 1, and we're going to make R to be 1. So here we can see the calculated gain matrix K, feedback gain matrix, and the closed loop eigenvalues are given over here. And here are the observer gains, and the observer eigenvalues are given over here. And this is the pre-compensation gain value that is calculated based on the value of K. So let us use this values and perform the simulation. So this is the response that we are getting. So let us do the measurements over here. We can see that we get a peak value of 205, magnitude 205.6, and we get a settling time of around 1 second. So yeah, this is the response when we keep the value of Q as identity matrix and R 1. Now, what happens when we increase the value of R? So we'll keep Q as it is, identity matrix, and we will increase the value of R. We'll make R to be 10. So these are the values now. You can see the new value of K over here. You can see the closed loop eigenvalues here. This is the observer gain matrix, and this is the observer eigenvalues, and this is the n bar. So let us simulate using. So this is the response that we are getting. Now let us check the measurements. Here we can see the peak time has increased. Now it is 206. Previously it was 205. It is 206 now, and the settling time has slightly increased, not much, slightly increased. Now let us check by increasing the value of Q. I'll make this value as 100 and I'll keep the lower value to be 1. Now let us see how the system response changes. Now this is the new gain matrix. These are the closed eigenvalues, the new observer gain value and the observer eigenvalues. So using these values, let us simulate once again. So here we can see the response. This look much faster as compared to, let us check with the measurements. So the peak over here is 193. Now the overshoot has reduced a bit, and the response time now it is somewhere close to 0.6. So the response time has become much faster. 0.7, sorry. The response time has become much faster as compared to the previous values. Now let us try and see the effect of reducing R. So I'll reduce the value of R to 0.1 and let us see what happens. So this is the new gain matrix. These are the closed loop eigenvalues. This is the new observer gain, and these are the observer eigenvalues. So let us simulate it. These values. See, now this is the response. So it looks very similar. Let us check with the measurements. Now the peak value is 189. So the peak has reduced. And let us check for the time. Previously it was 0.7. Now it is 0.63. So the response time has become faster in this case. So what we can conclude is we can change the response of the system by changing the value of Q and R. So as we increase the value of Q, so the system response becomes faster, and as we decrease the value of R, the system response becomes faster. On the other hand, if we increase the value of R, then the system response becomes slow. So this is all for uh, state feedback control method where the control gain is calculated using LQR.
So now hopefully you understand how we can design state feedback controllers and as well as how we can practically implement these controllers. Thank you.